Hello Critical Signals, thank you for having me. I wish I could be in Wellington with all of you right now. If you hear noise in the background, it's because it's a bit windy today. I hope it's going to be okay. Before I begin, none of the slides in this talk uses LLMs or AI or image generators. Everything has been handwritten or drawn, so you don't have to wonder. I am half of a little design studio called 100 Rabbits. We focus on the fallibility of modern tech. We've been working entirely from second-hand devices from the start. We were founded 10 years ago. We operate aboard a small sailboat. It's 10 meters long. It's called Pinot. It was built in 1982. This is our workspace, our habitat, our gym, our rec room, our bedroom, our kitchen. Our life is basically like we're camping all year long. We sailed to New Zealand a few years ago through Marquesas and French Poly, Niue, Tonga, and we stayed in Whangarei for 9 months. It was lovely. We started sailing because we wanted to live that sort of punk life according to seasons and learn more about repair and maintenance. We wanted to move between places in our own terms. The sailboat gave us that flexibility. But really, it came with a lot of challenges, and a lot of these challenges advised some of the things I'm going to be talking about today. I think in a way we've become sort of anachronistic to modern life. We sort of diverge from the general direction of things. To give you a sense of the limits that we have aboard, our solar power comes from two 100 watts solar panels. We store this in 4 lead acid batteries. They're like 6 volt sort of golf cart kind of things. With it we power all our laptops, all the habitat, all the lights, the things we need to survive, the safety systems. And in this talk I'll talk about the limits and the complexity and the appropriate technologies. And I think it's easy in this context to think like, oh well, you can like sort of engineer your way out of some problems by buying more batteries, which add more weight, which makes it harder for us to run away from storms, or like buy more panels, which adds more windage and more chance of capsize or hazards. And I think like managing this complexity and these limitations, I think it's important. But really, like, if you have the inclination of always buy more of X, usually it's gonna add more problems than it's gonna solve. And I'll try to explain some of the choices that we made and some of the conclusions that we found. So when we began looking for spaces that still build compatible tech for the way we were living, we found that modern tech is sort of at odds with the nomad life, even though it's easy to imagine that now everything is remote, but everything is also always online. Everything is 2-step locked, and you need an address, and it's harder today, I think, to live the nomad life, even though some technology seems like it would welcome this. It doesn't always. Inefficient software and always online software is sort of like, who still builds software today that works reliably offline? Who today still builds software that is written in an efficient way? How far back in the past do we have to look for these actual things these tools that we can use? Well, in that research, in that questioning, we found someone who highlighted the same pain points. This is an article I found a few years back, and it's the original Permacomputing article. It articulated perfectly the problems that we were having, and looking deeper into it, I found it was written by this artist called Visnut. His name is Ville Matthias, and he wrote about demoscene and ludism and digital aesthetics and the environmental impact of technologies. It was a pretty fresh vision of computation that was way different from the prevalent futurism that we see everywhere. He wrote this specification of permacomputing. I have it here. It's a practice that encourages the maximization of hardware lifespan minimization of energy usage and focuses on the use of already available computational resources. It's about using computation only when it has a strengthening effect on ecosystems. When I read these two sentences, I thought it was such a lucid enunciation of the problems and that we were facing. I immediately started to want to know more and found out who was behind this and if there was a community and who was exploring this sort of like what seemed to be the solution to our problem. We found communities, but also we gathered the friends that we have that are operating under similar constraints. And well, in fact, this is how we got in touch with Julian, who runs Collapsible System, which seems to be like another exploration of that space, and with hyperlocal solutions to problems. And so I would like to explain some of the ideas behind that permacomputing. The way I see it, obviously there are many ways of approaching this, but I've divided permacomputing into 3 stages. So I guess stages of adaptation relative to resource availability. So the way I'm going to break it down is going to be frugal, salvage, and collapse. So each stage is a step further away from available power, internet, hardware, and so on. The first one, by the way, these are not my words. It's sort of like things I found online that people use. I'll rephrase it in my words afterward. But like the definition of frugal computing would be utilizing computational resources as finite to be utilized only when necessary and as effectively as possible. So basically, like, this is about familiarizing yourself with using as little as needed while resources are just generally available. So it's kind of like learning to use a med kit while you're still in the city, so you learn about what's inside, but also if you made a mistake, you can course correct. It's always sort of better to practice preparation when resources are available than when it's too late and shit hits the fan and you don't have access to correcting. The second stage would be salvage computing. So it's about utilizing only already available computational resources to be limited by that which is already produced. So you can imagine the production treadmill has stalled, and what is produced is just more of what's already available. And the last stage is collapse, and it's about utilizing what has survived the collapse of industrial production or network infrastructure. So at that point, consumption is more like fighting over what's left, and most of what's already being produced is just sort of decaying. So it's more about maintenance, and at that point, you can't just run to the market and get a new one. So all right. So as we move through these 3 stages of adaptation, computation is used increasingly as a tool of control as the climate collapse worsens. So further down the descent, the more technical things get, and the more technology is something people have to actively engage with and understand, especially if it's forced upon you. So I guess permacomputation is like a framework for navigating this sort of language and also this sort of environment where things might not be as reliable as they once were. So I guess you can phrase it as a utopian ideal that requires doing a lot of rethinking and rebuilding and technological design and education to put it in practice. But I don't mean that people have to go like jump into learning at assembly, and there's much more proactive things to do first. I think also it's more something to be engaged in as a community than individual, so you can leverage different people, different skills. But really, the first things that can be done doesn't have anything to do with assembly. It doesn't even have to do anything with technological knowledge. It's about exploring the value of absence. It's finding where technologies do not have a strengthening effect on the ecosystem. It's also finding ways to do away with technologies that precipitates climate collapse. So like it's about stopping to produce things that can't be repaired. It's reducing technological waste. And further, it's getting rid of technologies that are clearly antagonistic, and sabotage them if possible. I think like going from finding where technology is not needed to finding where technology is like having a harmful effect, and moving beyond this is like finding where technology actually like can bring you where you want to go, and then it just vanishes in the background. Well, there's a perfect word for this, and it's called self-obviation, which is an aspect of technology that tries to make itself less and less necessary to the realization of its purpose. So gradually allowing people to provide for their own welfare. A technology can't both be emancipating and making you dependent on it. It's sort of like it has to, bring you where you want to go and just get out of the way. It can't start wedging itself in between people. And self-obviation in terms of technology is something that people should try for. It could be an engineering practice. And I'm gonna dive down further into this right now. So, permaculture, which is the first half of permacomputing, is about developing systems where nature does most of the work. So, for this to work, permaculture thrives in diversity. It uses load balancing of a diversity of solutions to create resilience. It's not about finding a silver bullet. There's not like a most permacomputing technology. Permacomputing technology is always going to be like a diversity of tech and products and people, and there's not it's not going to try to develop a monoculture of like a single crop for tackling a scale of problem. The first question that permacomputing asks is where technology is not appropriate. Where can it be removed by? Where can we do without? Because in most cases, technology is sold as a time saver, but really it isn't. It rarely saves time. It complexifies things a whole lot and makes people dependent on supply chains. It usually turns out to be a tool for controlling people and making sure that people don't understand the tool that rules their lives. They're made as opaque as possible, and in some cases they even will complexify things that are simple and make complex things seem simple. So in that process, they sort of obfuscate the waste, the byproducts, so people have no idea what's going on. And doing away with, identifying them, getting rid of them is like a really good first take and requires very little knowledge of the intricacies of computation. So if we stop forcing computers down people's throats, what we find is that, either we don't need computers anymore. I mean, there's definitely a case where a whole bunch of people's lives would be they would be happier, their lives would be simpler if computers were just not there, and if they were not forced to use them. But we might find that there's still a need for computers as ways of learning about the world, for games, for art, for music, whatever. But once we have identified where computation actually has a strengthening effect on the ecosystem, whether it's creating things, in most cases it will be benign tasks, and this is where permacomputation exists right now in the space. Obviously, when I say that people should understand the tools that they're dealing with, it's a sliding scale, right? So having the option to reverse engineer or repair a tool gives you leverage, and also it allows you to repair something when it breaks. But the agency that this gives you doesn't have to be individual dealing with this complexity all on their own. You can have someone that has the skills needed to repair something, but not having that option at all makes tools that will never be able to emancipate anything. So the way I've looked at this is that from the original permacomputing specification, it's basically just good engineering practices, and I'll walk you through some that I found are interesting. The first one is designing for disassembly. So designing for disassembly, I mean, it's what it says it is. Basically, it encourages repair. The idea is that a product can be taken apart at the end of its life, and each component can be reclaimed, basically. So designing things for disassembly has in hardware it would mean giving a manual or the instruction for the assembly and disassembly of the product, using parts that are not proprietary. In software, it means having the source file, the binary files, the good documentation, so people can understand what they're using and how it works. That makes a ton of sense in a world that has like spotty internet, for example. 100 rabbits, like the way we operate, for lengths at a time. We don't have access to internet, so we can't do tech support for the tools that we make. So people have to be able to disassemble them, find out how to solve their own problem. In some cases, we will turn up and have internet again and see that people have like reverse engineered or like used the docs and found ways to solve their problems without our interfering. I mean, if we had been available, we would have helped, but giving the option that if something happens to us, the tool is still usable, well, it's a pretty good tool for fighting bit rot in general cases. Another tip for engineering practices that align with permacomputing is to design for encapsulation. It's a bit more abstract, but really what it means is to be able to replicate the environment of a product. So you might not have the knowledge to understand how the product works or the internals of the thing, but if you can replicate its environment, it should behave the same way as it did before. So I guess like software emulation, for example, it recreates the mechanism of hardware. So like today you can run like a piece of software that was made for the classic Nintendo, for example. That is a form of encapsulation, so it allows us to preserve a piece of software through time, even though the source code was gone, even though we don't have the access to the internals and the logic and the design documents that made this artifact happen. We can still use it because we were able to replicate the environment perfectly. Encapsulation has like different facets to it. I'll explain a couple, just skim over this just so you have an idea of like what tactics people use in the past. The first one is migration. So basically, you convert a program from one operating system to the next. Like you've used Word for Windows 95. Well, then a new Word was made for Windows 98. The code was migrated. Most of the code, I'm pretty sure, was reused. So we can call that migration. Emulation is mimicking the behavior of older hardware. It's basically tricking old programs to think that they're running on their original platform. It's how we get to play, video games from the past, but also it's how Nintendo keeps churning out new versions of their old games because they just change the wrapper around it. Encapsulation, straight up, it means like containerizing. If you're familiar with Docker, all this kind of thing, it's about replicating. It's recreating the capsule, the environment in which the software ran, in a more abstract and in a more like higher level thinking. And the last thing is called universal virtual computer, and that one is more like defining, I guess, the axioms or the mathematics or the logic systems of a program. Basically, like it's about defining the program in abstract terms that will adapt to various ecosystems and should transcend hardware and software and any of that. I'll explain further in down the talk, but for example, this is one of the approach that we took as a studio to make sure that our software would keep running over time. I mean, as I mentioned, I'm pretty sure you have example that pops into your head, but like if you're like a programmer, you would think like Java, like the JVM is sort of an ecosystem that had the tagline for Java was like write once, run everywhere. And it's that idea, it's a strategy to fight hardware obsolescence. I think at that point, they were already seeing that they would have to rewrite the same program over and over and over again. And by targeting a virtual machine, they were allowed to write the program once and run it everywhere. Is Java permacomputing? I mean, it's less about finding, is something permacomputing or not. It's like that specific attribute of Java is appropriate for the situation here. It's appropriate for fighting obsolescence. I mean, I can't say if Java is permacomputing or not. That attribute, though, it is. If you use web browsers, you're probably watching this through Chrome or Firefox or something else. You might be thinking, well, browsers is one thing, right? Browsers is sort of like the GVM. It runs on all sorts of devices. But like all of these like virtual machines and encapsulation systems, it doesn't solve the whole problem. It usually comes at a cost of efficiency. For example, like web apps are super slow. Like most websites like do pretty simple things, but they consume maximum amount of energy and power. and web browsers come with like a whole swath of problems that, I mean, are beyond the scope of this talk. But is the browser, permacomputing? That's something that comes up quite a bit. Well, for one, the web specification can only be implemented by like 2 companies, and so that means the whole ecosystem has been captured by a handful of people. And building new web browsers today is unthinkable. And that makes that sort of like voids the compatibility with permacomputing on the bloat and the corporate capture. It makes it impossible for anyone to understand the tool, because the tool is growing at such a like logarithmic scale that there's no way someone's going to understand what the hell's going on, and that sort of makes it at odds. I think like one misconception that people often will straight up tell us is that oh well, like we don't want to halt the development of new tech because isn't it getting more efficient over time? Like I think that's a misconception that people have, that's sort of like, yeah, okay, like new hardware will do a lot more, but they will always use more energy. It's sort of like Devine would like it wouldn't work for us. A lot of time people suggest technologies for us that are seemingly more efficient. They're more efficient at doing like really complex things, which we don't do, but really inefficient in a way that makes it impossible for us to even run them on the battery power that we have. Alright, so and one last little engineering tidbits that I have is to design for descent, and that one's easy. It's sort of like it's designing things to degrade gracefully. So like when the power, like designing for when the power is low, designing for when connection is unstable, designing for one of the components fail. Like it's a engineering tactics that ensures that if the sound card of your computer fails, well, it doesn't take down the whole ship with it, and you can still use the rest. It's making sure that if the internet slows down, well, you can still use the tool. It's when you're running out of power, it starts to take less power. This ties to resilience. Resilience is applies to much more than computation, and I'll just like walk through like some of the, I guess, the 4 pillars of resilience. The first one is agility. So that defines it's the capacity to adapt and respond to changing environment. So like if something is too rigid, then it will not be resilient. Preparedness, that's just looking ahead, preparing, like having a plan. Elasticity is sort of like having flexible requirements and needs for the things to work properly. And redundancy is just having more of the thing in case one fails. Redundancy extremely useful aboard a boat. And I mean, like permacomputing didn't. I mean, even though the paper is just a few years old, it didn't invent the concept of digital preservation. It's just like a couple of people got around like this word, but really this has been a field of research for many years. The first one that I discovered that was doing some permacomputing adjacent, from work from the past, was PADI. It's like an Australian coalition team. I don't know, like a gathering of people who explored that problem. Cedar is another one. Chameleon is another one. Chameleon, the like objectives I found like it could have been in the permacomputing paper because it's so aligned. So the 3 main objectives of Chameleon was to explore the options of long-term retention of the original functionality and look and feel of digital objects. Fancy word for saying make software work tomorrow. And their second objective is to investigate technology emulation as a strategy for long-term preservation and access of digital objects. Well, it's what makes it possible today to run DOS games on your computer. It's like they were basically like exploring emulation as their tactic to preserve software. And their third objective is to consider where and how emulation fits in a suite of digital preservation strategies. So, like permacomputing, they didn't think that they would be like a silver bullet. It's more like leveraging different tactics for like maximum resilience. Unfortunately, all these projects are defunct, and it's only available through Internet Archive. and that doesn't speak well of people who had a lot of funding and also means to explore the space. If just a few years later we can't see any of it anymore. But that's sort of like the pattern when you start digging into these things. A classic example is the Domesday project. In the 80s, I think it's the BBC wanted to mark the anniversary, the 900th anniversary of a book called the Domesday Book, which was like a census of England, written by monks in the 11th century, I think. And it's this big book right now that sits in a museum that that some people can go and access and read. It's accessible and understandable today. So the BBC, in its honor, wanted to make this project that captures the 80s British way of life through music and videos and pictures and stories. And so they had this idea of encoding all this into these big proprietary discs. They figured people of the future will have disc players. By 2002, it was so hard to access this. All the drives were gone. People who worked on the project retired, and they were mostly undocumented. Chameleon worked on figuring out how to get this data back, but it was like the dawning realization that this is a fiendishly hard problem. They made all these projects and specifications and plans, and today none of it remains. But they are outliers. Like the '96 Space Jam movie website is still visible today, and it still works, and it displays just the same as it did in '96. And so, what can we learn from this? There seems to be a hard cutoff of usable archived media and technology after the Commodore and Macintosh DOS era. Somehow it's easier to run a project made 40 years ago than it is to run something that was made 10 years ago. That makes sense in a way, right? It's like we have a better understanding of how things worked back then, but also really the reason why we're permacomputing aesthetics is it seems like it's stuck in this bygone era is because permacomputing is about managing that complexity, and we probably don't have the tools today to manage the complexity of something that was made last year, but we do have something to manage the complexity of something that was made in the 80s and emulate it and run it at a reliable speed. But if all these organizations, all these exploration and these research projects and these academics couldn't make it work, so do we have any insights on what actually might actually work for doing this kind of preservation? Well, one thing that reliably works is piracy. Piracy has allowed games to survive when their authors has given up on migration or portability, and there are ways to run games today through piracy that runs 1,000 times better than the wrappers and emulators that the official emulators that people made. And 1,000 times is not a number I made up. I tried running Age of Empires 2 through an emulator that replicated the hardware in which it was supposed to be run is about 1,000 times faster than running the same game through the wrapper made by Microsoft. So piracy definitely has a role in this, and so what allows this for so obviously a massively popular project will have a massive following that allows it's more man hours, more people can spend time to fix and understand and reverse engineer and document these projects. But can we plan ahead? That is a question that I really like, and I really like to think about. But to understand how we plan ahead, I have to get way in the weeds here, but I think I found a way to explain it in a way that's kind of interesting, I hope. So complexity in the abstract, in computation, we can think of it like this. It's like the distribution of chaos. This sort of a complicated language, but on the slide here, there's two strings, two lengths of text. The one above is 424242. It's 12 times 4 and 2. So if you were to write a program that generated this text, it would be the amount of characters that you see underneath, right? So it would be def print A, print 42 times 12. So the length of the smallest program that can generate that string, that length of text, is a good indicator of the actual inherent complexity of that bit of data. Okay, the text below, where it's OJMD4XYO and so on. Well, since you can't infer or generate it by rules, you have to encode the whole thing, and so the programs to generate that bit of data is a bit longer. So in one we have, like a small program, and the other we have a bigger program, and we can say that complexity, I guess, in the abstract can be referenced to as like the length of the smallest program that can generate that bit of data. I have a better example for this, and it will just make this clearer. So on the left here, I have the lyrics of the song I Am Blue by Eiffel65. And on the right, I have the lyrics of No Regrets by Aesop Rock. The entropy of one is bigger than the other. If you've ever used a compression tool, like if you right-click a file and you zip it, well, the compression algorithm, in most cases, is something like exploring the complexity index of a bit of data, of any bit of data. So the complexity of, if we were to compress I Am Blue by Eiffel65, it ends up with the exact same algorithm in either case, and it ends up as 176 bytes, or 176 characters. And on the right, it's 348. So that means the song on the right is a lot more it's almost twice as complex. I mean, complexity-wise, and this is something that exists across all media. It's not just lyrics or songs. Like, I'm showing you here, like, basically it's two images. It's the binary representation. The binary is like a number 1 is a black pixel, a number 0 is 0, and on the left we have I Am Blue by Eiffel65, and we can see a repeating pattern, and mostly like the eye will notice instantly that there's less chaos in this one and on the one on the right. And this really like exists in audio and video and any sort of data stream. You can start comparing songs or pictures or diagrams or symbols or flags and notice how few rules, few axioms you can rely on to recreate that pattern or that logo or that design, and that's an indication of complexity. And this, when people talk about complexity in computation, that's exactly what they mean. In the concrete, though, complexity is something entirely different. It's basically how many lines of code that you need to migrate if you want to port your program, and if you want to fix a program, like the time that you will have to spend learning how a program works, the internal aspect of it, the line of codes is a pretty good indicator of like the complexity of something. And in almost all cases, the arrow goes up. There's a saying with boats, which aligns perfectly with software and hardware. It's small boat, small problems. Big boats, big problems. This is something that has been explored by a sailor called Roger Taylor, who sails a little boat called MingMing. Everything he writes about is fantastic, and one of his whole thing is about safety through simple systems, and resilience through redundancy and just planning. Anyhow, so resilience in computing is finding ways to manage this complexity. It's preservation is basically like studying the artifacts and working backward. But designing for preservation is figuring out the simple primitives that will generate the complexity further down the road. And if you manage this properly, well, it will lighten the load in the future. An example I love of this is the Arecibo message. It was an interstellar radio message for which that we basically beamed into space, and we don't know what the receivers, the potential receivers' capabilities are. So we can't infer. They don't have they don't know ASCII. They don't know English. We can make pictograms and stuff, but even sending pictograms through a radio signal, how do you even do it? So, like, you have to engineer things with robustness in mind, and so the way they figured it, I think it's a beautiful solution. Basically, like, the length of this message, the Arecibo message, is 1,679 bits. So it's basically the same as we were looking before, where we were looking at all the little bits for all the lyric songs. Well, in this case, again, a 1 is a black pixel, a 0 is a white pixel. There's 1,679 bits in this one. I mean, it's a tall rectangle. And the reason why they chose that specific length for a message is that it's a semi-prime. A semi-prime is made of 2 other prime numbers. So 1,679 can only be reached by multiplying 73 by 23. It gives the dimension of this image. So, I mean, we can't know that aliens will have a base 10 or base 20 or base 400 numbering system, but we can pretty much be sure if they have the technology to receive radio signals, they might have come across primes, and based on like primes, which are like something found in nature, well, they might be able to decipher the message that we're sending them. So that's a way of using robustness as a first design principle. So the addressable message is a message without a header. It doesn't have a data format really. It's just a bunch of bits basically. I mean, throughout the ages, like we've gone through a ton of file formats. Some of them more robust than others. The more complex the file format, the more likely they will stop being supported in the future. And the more interactive and multimedia, the harder it is to preserve. The Domesday Book, the BBC project, the complexity of that one was pretty high because it was music and video and all that, but it's even harder and more complex to maintain if it's a specification for an entire computer. And I mean, there were forays in this space, and it's a fascinating space for me especially. But right, so if we know all this, like, why isn't there someone that created the perfect computer system like that will preserve things in the future indefinitely? Well, in the 4 approaches of encapsulation, the last one was the UVM. The UVM is the idea of specifying a computer that would be so simple that would basically that will be so close to the natural rules of nature, or that can be specified in so few words that it has, through sheer ease of portability, a chance of surviving. So, in theory, writing software or writing anything that would work and be decompiled or deciphered through a system like this would be the easiest. But it's always a trade-off. You're always sort of balancing this trifecta of portability. I mean, like a system as small as this one here. It's portable because it's easy to migrate. It's resilient because the specification fits on a napkin, but it's very slow because it does atomic operations that can't utilize the system's hardware. So you're always sort of like shifting this sort of irreducible complexity and not doing any headway. And most systems that were designed for like archival and long-term preservation are just not used because they're so inefficient. So we're in this middle space where you're sort of like exploring this boundaries between suffocating minimalism and unsustainable maximalism. Computation is about managing state and the vast number of permutations that a specific length of memory can take. At this point, we're like increasingly diving faster and faster into larger and bigger universes of state, and we've not even begun to explore the one that we just left. And Permacomputation is an invitation, basically, to slow down and to make sense of where we are and to explore what's possible with what's already here, to prepare with what could happen. It's an invitation to participate and to learn to control the tools so that they don't control us. Well, thank you so much for having me. I hope that I've inspired you to become interested in exploring what could help make computers last a bit longer. Thank you so much. I'll stick around for a QA. Have a